And the last thing are functional groups. So functional groups are a lot like the secondary chains that we talked about, except instead of being alkanes or alkenes or anything like that, they are completely different structures. So these will involve other elements than just carbon and hydrogen. The functional groups we're going to talk about are alcohols, ethers, aldehydes, ketones, and carboxylic acids. There's actually in organic chemistry about 17 functional groups. We're just looking at these 5 though. The first one is an alcohol. So obviously you've heard the word alcohol. It's in a bunch of different places. Alcohol is not just a single thing. There's different types of alcohols. Methanol, ethanol, and propanol are the 3 most common. Methanol would be what they use a lot of times in antifreezes, and you don't drink that. Back in the day when they used to make moonshine, they would call methanol would be wood alcohol, and if you drink it, you go blind. Ethanol, that's the drinkable version of ethanol. That's the kind that's in beer, wine, and liquor. Propanol would be rubbing alcohol, so if you buy rubbing alcohol at the pharmacy, that would also be one of your choices. That is also not drinkable, will kill you as well. And alcohols have your carbon chain, and at the end of the carbon chain, they have that OH group. So all of these have that OH. Looks like a hydroxide, but it is not a hydroxide. It is covalently bonded on this side, which means it does not branch off into an OH minus. So don't get these confused as a base. That hydroxide, that OH group, that's an alcohol functional group, and it does not come off. Naming these guys, so this right here would be methane, and it's methane with an OH group on it, so we drop the A and E and add an OLE, A and OLE. So methane becomes methanol, propane or ethane becomes ethanol, propane becomes propanol with that OH group. And if we put that OH group off of a benzene ring like this one, the phenyl with the alcohol is called a phenyl. And this one should be one that you recognize, and you've actually heard it in several different places. If you look on cough drops, those white cough drops that you take, they have menthol in them, and that's that kind of cold taste that cough drops will give you. And another way that you'll see it is cholesterol. Cholesterol has that phenyl in it, and that's what makes it really bad for us because it's big and blocks things up. If we have just 2 carbons, naming the ethanol or naming the alcohol is pretty easy. We just count the carbon chain. So this first one has 2 carbons. 2 carbons would be eth, and so 2 carbons with a alcohol group would be ethanol. This last one down here, though, or these last 2, both of them have 3 carbons, but the the alcohol functional group is located in a different place, and so we have to specify with the numbering method. So we're going to number this one as 1, 2, and 3, and this one is 1, 2, and 3 as well. And so this first one, this middle one, the group falls on the first carbon. It would be called 1-propanol. With the 3 carbons, and then the second one would be called 2-propanol. Once again, same formula, but the difference, they're going to have slightly different properties and different naming. They would be considered then isomers. We would in practice call this one a primary alcohol because the alcohol group is on the primary carbon, and this one right here would be a secondary alcohol because the alcohol group is on the second carbon. Next are ethers. Ethers have an oxygen planted nice and firmly in the middle there. So you've got your carbon chain on either side and then oxygen in the middle. So here is 3 different versions of ethers. This first one would be dimethyl ether. So dimethyl, why? Oh yeah, because it's got 2 ethyls on either side of the ether. Sorry, that shouldn't say ethyl there. That should be dimethyl ether. This second one that we see right there, you've got your ether because there's the oxygen firmly planted in the middle. We have 1, 2 carbons on that side and 1, 2 carbons on that side. That means we have 2 ethyls. So this one would be diethyl ether. And the third one, there's our ether group, and on the left side we've got 1 carbon, on the right side we've got 2 carbons. That would make this one methyl ethyl ether. Isn't that one kind of cool? Methyl ethyl ether. You should name a kid or a dog or a cat or something that. And all of these structures are bent with a 104.5 degree angle. If we were to draw this more similarly to represent Vesper, you'd have your oxygen with its two lone pairs coming off like that, and then you would have your carbon chains over like that. And so the angle between all of these would be 104.5 degrees. Even though we draw them in a nice pretty straight line like that, they're not really straight. They're going to be bent around that ether. Diethyl ether, this middle one right there, was actually used a lot back in practice. If you ever heard the word ether, you're probably thinking of the anesthetic that they used to use, and diethyl ether was the original anesthetic for surgery. The problem with it was, and the reason they don't use it to this day, is some people wouldn't wake up after they knocked them out with it, which is a problem for lawsuits and things like that. Because of this bent structure, diethyl ether has very, very low forces, intermolecular forces, which means it boils at a really low temperature. It actually boils at 34 degrees Celsius, which is just a little bit above room temperature. Room temperature is considered about 30, 25 in there. So if you hold a flask full of diethyl ether in your hand, it will literally start boiling in your hand, which made it good as an anesthetic because it would gasify really easily so they could get people to breathe it in, give them their surgery, and just pray that they woke up in the end. And the next one is an aldehyde. So an aldehyde, at the end of a carbon chain, you replace one of the hydrogens with a double bond to an oxygen. So instead of having on your last carbon all of those three hydrogens, you wipe out one of those hydrogens and replace it with a double bond to oxygen, and that makes it an aldehyde. But it has to be on the last carbon. It's not one of the middle carbons or anything else. This first one right here, since that's meth, instead of calling that methane, we replace the E with an AL, so it would be methanol. Methanal is how we would pronounce that one. And the second one, that's an F, so instead of ethane, it would be ethanol. Methanal, this first one, that's actually formaldehyde, which is what they used to use to preserve bodies and specimens, but it's also a known carcinogen, so they went ahead and quit using it. And next is the ketone, which looks a lot like an aldehyde. The difference is that instead of the double bond to oxygen being on the last carbon, it is now on one of the middle carbons. So on this general structure up here, this general formula, there would be other carbons attached on either side of it, going off in a chain. So it's not going to be the final carbon. This first one right here that we look at, see how the carbon right there has two carbons on either side, and then the ketone in the middle? This first one is called propanone. So ketones are named with the anone at the end. So this one's propanone. We don't need to specify where the ketone group is, because if we were to move it over here, it would become an aldehyde, and if we were to move it right there, it would become an aldehyde. So there's only one possible place for the double bond to fall on a propane backbone. However, with this one right here, notice how the double bond is on the second carbon. We could take that double bond and move it to that carbon, and it would still be a ketone, but it would kind of change the layout. So since this one is on the second carbon, what do you think we name this? If you say 2-pentanone, then you would be correct. 2-pentanone, because the double bond falls on the second carbon. And all of these are going to end up being trigonal planar around that carbon, because if we think about this, you've got the double bond, and then you have your two single bonds on either side. That's going to make that trigonal planar shape with a structure of about 109.5. A place you've probably seen this term or familiar with this name is testosterone. That O-N-E at the end implies that testosterone is indeed a ketone. And last but not least, the carboxylic acid. So the carboxylic acid has on the final carbon the double bond to oxygen, like from an aldehyde, and an OH, like from the alcohol. So it's actually a combination aldehyde-alcohol, where we have that double bond to oxygen and the single bond to OH. Remember that OH right there is not a hydroxide, so this is not a base. Instead, it's actually an acid. So this first guy right here, that is methanoic acid, because you have the methane with the acid, and so we call it methanoic acid. The second one, that is a butane group or butane group, and since it's an acid, it's butanoic acid. We don't need to specify where the acid group is, where the carboxylic acid is, because it's always at the end. It always has to be at the end of the chain. So thinking back to acid-base chemistry, what makes this an acid? So an acid is something that generates hydroniums or produces those H pluses inside of a solution. When you put a carboxylic acid inside of water, it's going to transfer one of its protons over to the water, and it's this proton right here that it loses, not this one. So it's going to transfer that H, making it this CO2 minus, so this would have a negative charge, and giving you your hydronium as a result. So the hydrogen that falls off in an acid-base reaction would be the hydrogen on the end of the carboxylic acid. Alcohols will not do this. What makes that hydrogen right there loosely attached to the carboxylic acid is kind of the pull of the electron density over this way, and so it's going to mean that hydrogen doesn't have a really strong attachment to that oxygen and can easily fall off in solution and generate that lower pH.